All right, ladies and gentlemen, this is section 3.1, the derivative in a tangent line. And here's the deal. I've probably done this on video now probably 30 times, and it's just so hard to explain with a tablet, but I'm hoping that the 31st time I'll get this right, okay? Here's what it says. Estimate the slope of the tangent line at x equals 1. All right, so here's my 1, all right? And the coordinate for this is 1, 1, because if you input 1 into this x squared, you get 1. And while it says y equals x squared, I could call this f of x equals x squared, and that would probably be trusted as pretty close to the same thing, okay? Now remember what a tangent line is, whether we're talking about a curve or a function, or maybe even a geometric shape from geometry. A tangent line is when you intersect your curve at one location. All right, now let's see if I can pull this off. That looks okay. Now, how do I find the slope of that? Well, typically we find slope using a slope formula. Y minus y1 all over y2 minus y1 all over x2 minus x1. That is typically our slope. All right, now you're looking at that and you're saying, I only got 1 point. How do I do this if I only have 1 point? Good question, all right? And so what I'm gonna do is this. Let's just have a generic point here. I'm gonna call this xy, all right? And in fact, I'm gonna change that. I'm gonna call it xy. I'm gonna call that x f of x. Make it a little bit more mature in terms of our way of representing functions, okay? And what I'm gonna do is I'm gonna pick a different point up here. Now, I know that this is what I prefer to recognize as a tangent line, but let me draw a secant line. Okay, now, to do that, if I'm calling this x and f of x, this specific point, I'm gonna call this something a little bit different. And the way I can address this, okay, and label that is based off of how much I'm moving in the positive direction horizontally, okay? And I'm just gonna say this is some change of x, okay? And change of x is delta x. And so if the original amount was x, and I'm adding some delta x here, this entire distance for this new point would be called x plus delta x. Okay, now that is this length going to the right, just beneath this respective point that I created. And so I will call that x plus delta x. And to find the corresponding y, or function value, what I'll say is that is f of x plus delta x. Okay, now here's the idea, and this is going to be impossible, almost impossible for me to draw. This is a point that almost crosses it pretty well. That's the equation of a line for, for a secant line. And you can see the secant line does not look too close to this tangent line. Okay, it's like, well, I can't estimate this to be the same as that. They're kind of a little bit off, okay? However, here's what I can tell you. I'll do this with a different color. Let's pretend for a moment that this delta x is a little smaller. Okay, which means if I only go out to here instead of where I originally said it would, that means my x plus delta x and f of x plus delta x is here. And if I were to draw the secant line between this point and this red point, I don't know if I can do it well. okay? What you find is that, that's a little sloppy, but what you find is that this secant line is a little bit better estimate for this tangent line versus the original secant line that I had, okay? And that was a result of making this little delta x smaller, okay? And the idea is if I make that delta x even further tiny, okay, maybe make it this tiny, okay, then what that means is my 2 points will line up right here, and I'll get a secant line that is even closer to this original tangent line, okay? And so what I'm going to do is represent this through a formula, which you may have seen in the past, and I'm going to take the slope, okay? Now the slope is y2 minus y1, so it's this monster f of x plus delta x, okay, minus y1, which is f of x, okay, all over x2, okay, minus x1, which is just plain x. Okay, and what am I going to do to this? Well, we said as our secant lines were provided by delta x's that got smaller, that it provided a line with a slope that was closer and closer to the tangent line. As these values got closer and closer to my original point of tangency, that the secant lines approached the slope of what this tangent line would be. Okay, and that was all a result of our delta x getting smaller. So what I'm going to write out front is the limit as delta x goes to 0. Okay, and that's how we come up with what we called the slope of a tangent line. Okay, and if I simplify this just a little bit, all right, the top cannot be simplified. You don't distribute the f through. I know some people think that. It's just, remember, these are input values. It's not distributing. Okay, minus f of x. And on the bottom, your x and your subtract x will go away. All right, so the idea is that this, again, is your original slope formula that we have right here, okay, based off of some change of x that differentiates the 2 points that I have. And the idea is that this delta x gets smaller, that this point along the curve will travel closer and closer to this original point, and the lines that are made for slope will get more and more flattened in this case, and will approach what that tangent line would be. And so what we do out front is we say, hey, we're going to take the limit as this delta x that we keep writing here gets closer and closer to 0. Okay, are you ever going to have to explain that? You're not, but sometimes people are like, where do we get this formula? And we're going to use it quite a bit in this lesson, and I just wanted to make sure that you had some idea of how it originated. I got it right that time. I don't remember what time I said that was, but that was a lot of attempts. So, all right, estimate the point of tangency here. So this is what's kind of nice. You're not going to have to use the formula. They're just asking you to look at this and take a guess. Did I even answer the question? Sorry, it looks like estimate the point. I'm going to guess that it looks something a little bit bigger than 1. It is actually something probably close to 2, if not 2, and you'll figure that out a little later. I wrote that. Okay, good. All that, and I forgot to answer the question. All right, estimate the point of tangency. So here's what you got. You have this nice curve here, and they ask you to estimate the point of tangency at A. And what's cool is they draw that line in for you, so I didn't have to make some strange attempt to do it. And what you gotta do is estimate the slope. And as I look at this, well, notice that B is already identified on a nice coordinate, 1, 2. And all I'm gonna do is count up from A to B as we go from left to right, okay? And my slope is, well, this increase up is a positive 2. And then from here, you're moving to the right 1. Okay, so my estimate for this respective tangent line should be 2. And if I were to look at this one here, you're actually finding the point of tangency at this A as well. However, your point of tangency for this line is actually decreasing. Okay, so and because of that means I'm going down 1. And this is to the right, looks like 5. Okay, so my estimate for my slope would be -1/5. Excellent. All right, so if those make sense, okay, let's move on.